Hello, students, and welcome to our discussion on oxidation reduction reactions, also called redox reactions. You'll need to take a look at your 8-17 notes as we introduce this seventh and final reaction type that we'll be discussing. This is the last of the seven as we move to closing up Unit 8's notes. What are oxidation reduction reactions? Well, it's a special type of reaction that includes many types of reactions. It is a very general category of reactions. In an oxidation reduction reaction, what happens is control of electrons changes. To really take a look at who is controlling an electrons in a chemical reaction, they've created a number called an oxidation number, also called an oxidation state. So we'll start off our discussion introducing the idea of oxidation numbers, again, also called oxidation states. For molecular compounds, oxidation numbers are really just trying to indicate the general distribution of electrons being shared between bonded atoms. When they're talking about distribution, they're talking about who is trying to hog the electrons. Remember, elements that have higher electronegativities are better at pulling electrons to them. They're better at tugging electrons so that the bonded electrons are spending more time around the stronger atom. So electronegativity plays a big part of understanding of oxidation numbers. For this reason, the very last page of our 8-17 note packet is an electronegativity table that you'll need to refer to when we're determining oxidation numbers. So again, for a molecular compound, that is a compound held together by covalent bonds. What we're really looking at when we're assigning oxidation numbers are who is going to be dominating the control of the electrons by pulling them to them as a result of having higher electronegativities. An atom, and a molecule that is able to pull the electrons to them and control the electrons the majority of the time would have a negative oxidation number. The element with a lower electronegativity that is not able to hold the electrons to it would have a positive oxidation number. And the actual number itself would refer to how many electrons are being controlled. So if an atom is pulling 2 electrons to it, it would have an oxidation number of -2. If an element is like fluorine is only pulling 1 electron to it, it would have an oxidation number of -1. Strong metals tend to have strong nonmetals in a molecular compound, they would have, again, a negative oxidation number. Fluorine's the strongest at 4O, so it will always get his -1 oxidation number. Oxygen is 3.5 electronegativity. It's the second strongest element of it all. So most of the time, unless it's with the fluorine, it's going to be a -2. The next two strongest are chlorine and nitrogen. Chlorine only needs 1 electron. It's in family Roman 7. So it would have an oxidation number of -1. Nitrogen, being 3O, the third strongest, it needs 3 electrons since it's in family 5. It would be a -3 oxidation number. So your oxidation number goes to, the negative oxidation numbers go to the more electronegative element, and the number they actually have corresponds to how many electrons they are trying to hog. Oxidation numbers are not saying that these strong nonmetals have stolen the electrons. They're just indicating how many electrons they would like to steal if they could, in order to satisfy the octet or duet rule. How can we recognize the difference between oxidation number and an actual ionic charge? Once again, we know fluorine is the strongest element with a 4O electronegativity, and we know fluorine wants one electron. It starts with 7. It's in the halogens. They all start with 7. They're in Roman 7. Fluorine needs 1 to satisfy the octet rule. In the compound oxygen difluoride, OF2, we have to take a look at their electronegativities. Fluorine is 4O, oxygen's 3,5. Their difference in electronegativity is 0.5, so that would be a very weak polar covalent bond. So fluorine is going to have trouble stripping the electrons and becoming ions. So this would be a molecular compound. So oxygen would be sharing with the fluorines. Fluorine, again, is the strongest here. It's a 4O versus oxygen's 3,5. So fluorine will get its -1, meaning that each of these fluorines would be -1. The oxygen, on the other hand, since it's with 2 fluorines at -1, that means that there's going to be 2 electrons of oxygen being hogged by the 2 fluorines. That would result in the oxygen having an oxidation number of +2. So by convention, and we mentioned this earlier this year, when the electrons are not actually transferred, fluorine here has not pulled the electrons off. When we're just indicating how many electrons it would like to remove, but it doesn't have them yet, they write the charge followed by the number. So it's -1. The minus first is indicating it doesn't have them, it just wants them. Oxygen has not lost 2 electrons here, but it is having 2 of its electrons being hogged, so they write charge followed by the number. Earlier this year, we realized that when we have a full charge, when the electrons are actually transferred, they would write the number followed by the charge. So in the compound NaF, sodium fluoride, this is an ionic compound, a metal with a nonmetal. Fluorine is 4O, sodium's around 0.9. The difference here is 3.1. That is 100% ionic. So fluorine will steal electrons off sodium, becoming the fluoride ion. How many electrons does fluorine need to steal to become fluoride? 1. So it would acquire a 1- charge. The sodiums would absolutely lose 1, becoming 1+. So when we are writing an ionic charge, it is number followed by the sign. You can also write oxidation numbers. Oxidation numbers are talking about who is controlling the electrons. Well, fluorine here is not actually only controlling them, it actually ripped it right off. But still, it controlled 1, so it's -1. The sodium's oxidation number is +1. So you can write oxidation numbers for salts, for these ionic compounds, but when you're writing it as an oxidation number, it's charge followed by number. When you're writing it as a full ionic charge, you write number followed by charge. So once again, we can write oxidation numbers for ionic compounds, but it's essentially the same as the charge. The anion has taken electrons. We know how many electrons it's taken by its ionic charge. Its oxidation number would just be the same, except you write charge followed by number. Now, what is another difference between oxidation numbers and ionic charges? Well, oxidation numbers, they really do not have a physical meaning because the electrons are not being transferred. They're just being shared unequally. So an oxidation number is not really telling you anything that's physically happened. It's just a number saying how many the atom wants or needs to become stable. Elements with high electronegativities are good at having negative oxidation numbers. Elements with low electronegativities are good at having positive oxidation numbers. Ionic charges, on the other hand, do have a physical meaning. Ionic charges are actual charges that have resulted from the transfer of electrons. So how do we write oxidation numbers or oxidation states? There are generally 10 rules that are followed. First rule, rule number 1, atoms in a pure element, including diatomic elements or elements that have like P4, phosphorus, or S8, sulfur in its elemental state. Well, atoms in their elemental state have oxidation numbers of 0. This is because an atom cannot hog electrons from another atom having the exact same electronegativities. They're equal strength, so neither can hog them, so their oxidation number is 0. Again, oxidation numbers refer to how many electrons are being hogged. The negative one goes to the one hogging, the positive one goes to the one that's having its electron hogged. For binary molecular compounds, the oxidation number for the more electronegative element will always be the charge it would acquire when ionic bonding. The less electronegative element would be assigned a positive charge. So here we have the compound ammonia, NH3. Nitrogen's electronegativity is 3O. Hydrogen's 2,1. So in this compound right here, nitrogen is the stronger of the two. So we know nitrogen's in family 5. So it needs 3 electrons, so we assign it a -3. We have 1 nitrogen here, so the total oxidation state is -3. That means the total positive has to be +3. There are 3 hydrogens here, so each of the hydrogens would have an oxidation number of +1. 3 divided by 3 is +1. We are not saying here that the hydrogens have had an electron ripped off. All we're saying is that 1 electron on each of the hydrogens is being hogged for a total of 3. Rule number 3. Fluorine always gets its oxidation number of -1. It has the highest electronegativity. The element in a compound that has the highest electronegativity is the one we assign first. So fluorine would have a -1. It's in family 7. It needs 1. The only time fluorine doesn't get a -1 is when it's with another fluorine in F2. In that case, it would be 0, as we mentioned in rule number 1. Oxygen is the second strongest electronegativity at 3,5. So oxygen will generally get a -2. It's in family 6. Oxygen needs 2 electrons to get stable, so it gets an oxidation number of -2. The exceptions here would be when oxygen is with fluorine. Fluorine gets the minus. Oxygen would then be a positive. So in OF2, fluorine gets -1. We've got 2 fluorines for a total of -2. Once again, oxygen would be a +2. Another time when oxygen doesn't get a -2 is when it's with another oxygen, such as the peroxide ion. The peroxide ion, if you remember, is O2, 2-. That means each of the oxygen atoms in the peroxide ion are 1-. They would have, that gives them an oxidation number of -1. When oxygen's with another oxygen, it would be 0. So oxygen has a 0 in its elemental form. Hydrogen usually is a +1 when it's with a more electronegative element. So when hydrogen's with other nonmetals, most other nonmetals are stronger than hydrogen. So it would get a +1. The ones that aren't stronger are boron, silicon, arsenic, phosphorus, and tellurium. So when hydrogen is with those elements, it could potentially have a minus oxidation number. Hydrogen does get a minus oxidation number when it is with any metal. And in that case, hydrogen would end up with a minus oxidation number. We'll finish up the next 6 rules in the next video. So we're going to stop right here for now, and we'll pick up with rules 6 through 10 on our next video.